Hello, everyone, and thank you for joining me today. We are diving into Chapter 5, the production process and cost, a topic that sits at the heart of managerial economics, whether you are in manufacturing, services, or tech. Understanding how to efficiently transform inputs into outputs is crucial for running a profitable business. In today's session, we will equip you with the economic tools you need to analyze production choices, manage cost, and make strategic decisions that align with business goals. So let's get started. First things first, learning objectives. To begin, let's review our learning objectives for this session. We will start by understanding how to measure the productivity of various inputs and outputs and how managers can influence the productivity. Then, moving on, we will explore how to calculate the demands for inputs using isoquant analysis and identify the optimal production functions. We'll also look at how production function translates into cost functions, and we will clarify the differences between economic and accounting cost. Finally, we will cover fixed, variable, and marginal cost as well as economies of scale and scope. The holistic view will help us build a strong foundations on chapters ahead. Why this matters? So, let me ask you a question. Why does all of this matter in a real world business settings? Well, managers are constantly making decisions about how to allocate resources, whether it's hiring more staff, upgrading equipment, or launching a new product line. A solid understanding of production and cost theory allows managers to make these choices wisely. For example, knowing your marginal cost helps determine optimal pricing. Recognizing when you are facing diminishing returns tells you when to stop expanding. Mastery of these concepts enables smarter operational planning, reduces waste, and create a sustainable competitive advantage. Let's take a real world example here. Tesla's production strategy. Tesla doesn't just assemble cars, they have vertically integrated nearly every aspect of their production process, from battery cells to vehicle manufacturing. This reduces reliance on third party suppliers and allows them to control both quality and cost. Tesla also invests heavily in automation. While this raises fixed costs due to capital investment in robotics, it ultimately lowers variable costs like labor. Their gigafactories are perfect example of economies of scale as they produce massive volumes at a lower average cost per unit. This strategy this strategy isn't just about innovation, it's about employing sound economic principle. Eng- Engagement question. Okay, let's pause for a quick thought exercise. What do you think happens to cost as production scales up? You might say costs go down, and that's often true, but not always. In the short run, firms benefit from spreading fixed costs over more units, but in the long run, managing a larger operation can become complex. You may run into coordination issues, communication delays, or bureaucratic inefficiencies. And what about service based industries? Do they scale as easily as manufacturing? Keep that in mind as we go further. Production function fundamentals. Let's talk about the production function, which is the mathematical representation of how inputs are turned into outputs. It is often written as Q equals L K M, where Q is output, L is labor, and K is capital, and M might include materials or technology. This function is more than a formula, it's a planning tool. It helps manager estimate how many workers of machines are needed to hit a target output. It also reveals how efficiently a firm uses its resources and serves as the foundation for both cost analysis and profit maximizing strategies. Production process flow. Here's how it works in practice. Firm begins with inputs like labor, capital, raw material, and technology. This inputs goes into a transformation process that includes physical manufacturing, digital processing, or service delivery. At the end, we get outputs. That means finished products or services ready for sale. The goal is to create value, meaning the output should be worth more than the combined cost of inputs, whether you are making a shoes, running a software company, or managing a hospital. This transformation is the essence of what businesses do. Short run versus long run. Now, we distinguish between short run and long run production decisions. In short run, some inputs like capital or equipment are fixed. You might be able to hire more workers, but you can't build a new factory overnight. This limits flexibility. In contrast, the long run is a planning horizon where all inputs are variable. You can redesign processes, build new facilities, and adopt new technologies. Understanding this distinction is crucial. Short run decisions are about optimizing within constraints, and long run decisions involve strategic change and investment. Production curves explain. To visualize this, we use three key production curves. The total product TP curve shows that the total output for a given amount of input. MP, which is marginal product, tells us how much extra output we get from one more unit of input, like one more worker. The average product AP is the total output divided by the number of inputs. Initially, adding input increases output rapidly, but eventually we hit diminishing return point. More input leads to less additional output. This is where the MP curve starts to fall, followed by the AP curve. Law of diminishing returns. This brings us to a foundational economic principle, the law of diminishing return. In the short run, as you add more of a variable input, say workers to a fixed input like machinery, there comes a point where each additional worker contributes less and less to the total output. And if you keep adding workers, output may even decline due to overcrowding or inefficiency. This concept helps managers decide how many employees or resources to deploy before hitting that inefficiency threshold. It's all about finding that sweet spot where productivity is at its peak. Let's take another example here. Too many. Think of a small restaurant. Let's say kitchen. If there are two chefs, things run smoothly. Add a third, maybe it's even better. But what if you add a fourth or sixth? Eventually, there's not gonna be enough space, and people start getting in each other's way. Productivity falls. People start getting in each other's way. Product. How about This is the classic case of diminishing returns in action. How about an office with one printer and 10 employees constantly lining up to use it? Or a construction site where more workers lead to a congestion and safety risk? Can you think of another real life scenario? Feel free to share one, please. Moving on, let's look at specialized type of production functions which help modern real world scenarios. First is a linear production function where inputs are perfect substitutes. For example, a company might be able to use either manual labor or automated machines for packaging. Both achieve the same results, and you can substitute one for the other depending on the cost. Then we have Leontief production function, as you can see, where inputs must be used in fixed proportions. Imagine needing one pilot for every plane, or adding more planes without pilots doesn't increase output. Each function has a strategic implications for input flexibility. Let's look at Cobb-Douglas production function. One of the most useful production models in economics is the Cobb-Douglas production function. It is often expressed as Q equals A L A K B. Here, A is a constant that reflects overall productivity, while alpha and beta are the output elasticities of labor and capital, respectively. What's powerful about this model is how it reflects real world trade offs. If A plus B equals 1, we have constant return to scale. If it's greater than 1, that indicates increasing return. Adding more input results in more than proportionate output. Firms can use this model to assess scalability and efficiency when planning production expansions. Understanding. Let's explore isoquants. An isoquant is a curve that shows all combinations of two inputs like labor and capital that yield the same level of output. Think of it like a topographical map for production. If you reduce the use of one input, you need more of the other to maintain the same output. Isoquants are downgraded sloping because of this trade-off, and they are convex to the origin, reflecting diminishing marginal rates of substitution between inputs. Higher isoquants represent higher level of output. This concept is central to identifying the most efficient input combination. Now let's bring in isocost lines, which are similar to budget lines in consumer theory. An isocost line shows all possible combinations of input that can be purchased for a given total cost. The equation is C equals WL plus RK, where W is the wage rate and R is the rental rate of capital. The slope of the line minus WR represents the rate at which one input can be traded for another based on their prices. If wages increase, the line gets slimmer. If capital costs drop, it becomes flatter. This shift affect how firms allocate their resources. Output input mix. Tangency condition. The optimal input mix, the combination that produces a given output at the lowest cost, occurs where an isoquant is tangent to an isoquant line. At this point, the slope of the isoquant, which is marginal rate of technical substitution, equals the slope of isoquant line, which is the input price ratio. Here's a graphical example to illustrate what we just discussed. We have two isoquants, one representing output level Q equals 100 and another for Q equals 200 and the respective isocost line. The tangency points represent the cost minimizing input combination for each level of output. As output increases, firm moves to a higher isoquant and may need to adjust their input mix. Visual tools like this help managers understand how production and cost interact, especially when input prices or output targets changes. Let's take that bakery example to see what is the difference between labor and capital. Let's apply this to a relatable business, a bakery, okay? Suppose the price of renting ovens increases. The bakery may respond by hiring more bakers and relying on labor intensive methods. On the other hand, if the wages increases, the bakery might invest in automated mixers and conveyors, ovens to reduce labor needs. In both cases, the firm is adjusting its input mix based on relative input prices. The key takeaway is that cost minimization is dynamic. It depends on market condition, technology, and resource availability. Cost minimization rule. To minimize production cost while maintaining output, firm follows the cost maximization rule, which again is MPL equals MPKR. This means that the last dollar spent on labor should yield the same increase in output as the last dollar spent on capital. If not, the firm is overusing one input and underusing another. This principle helps firm adjust hiring decision, capital investment, and operational process to keep cost as low as possible for any given level of output. Marginal rate of technical substitution. To close this section, let's expand on MRTS, which measures the rate of at which one input, say labor, can replace another like capital without changing the level of output. The marginal rate of technical substitution is equal to the ratio of marginal products of the inputs or MPL MPK. In the real world, MRTS reflects how flexible a firm is in its input choices. If labor is cheap and abundant, you might shift away from capital. If labor is scarce or expensive, automation may be better investment. Marginal rate of technical substitution gives manager a framework to adapt their operation efficiently as conditions evolve. This graph shows us a dynamic situation, which what happens when input price changes. Initially, the ISO cost line is set based on original wage and capital cost. Now imagine wages increase. This shifts the ISO cost line inward, the point where the new ISO cost line is tangent to the isoquant represents a new cost minimizing input mix. The firm might now use more capital and less labor. This is a practical example of how price changes affect input allocation. Managers must constantly monitor these changes to keep operations cost efficient. Replacing labor with automation. Let's take the example of traditional car manufacturing. Decades ago, these plants were filled with workers assembling vehicles by hand. But over time, as wages rose and automation technology became more affordable, firms began investing in robotics. While automation has high upfront cost, it significantly reduces ongoing labor expenses and increases precision. The decision to automate hinges on input prices, the marginal productivity of each input, and how flexible the firm wants to be. Some firms may prefer hybrid systems, balancing labor and capital depending on output needs. Now, let's shift to the cost function, which links production decision directly to dollars. A cost function tells us the minimum cost required to produce a specific level of output. It's written as C equals FQ, where C is the total cost and Q is output. This tool is powerful for decision making because it helps estimate cost under different scenarios, like changing prices, scaling output or adjusting input combinations. Cost functions are central to profit planning, pricing strategies, and budgeting models. In the short run, we deal with both fixed and variable cost. Fixed costs like rent or salaries do not change with output. Variable costs like raw material or electricity rise as output increases. The total cost is simply the sum of fixed and variable cost. TC equals FC plus VC. For example, a bakery pays 2000 in monthly rent, whether they produce 10 or 1000 loaves, but their flour and labor cost rise with each loaf baked. Understanding this breakdown helps manager control cost behavior and demand fluctuates. Let's summarize these costs in a quick table. Fixed costs remain the same regardless of production like rent variable cost. To, like okay, I'm sorry there's been a problem with my finishing. Alright. So total cost equals both combined. This framework helps manager identify which costs are controllable in the short term and which are not. When demand drops, variable cost can be reduced, but fixed cost remains. A critical insight when considering scaling up or down. Average and marginal cost are central to understanding cost efficiency. Average total cost is total cost divided by units produced. Average fixed cost falls as output increases because you are spreading fixed cost over more units. Average variable cost reflects per unit variable expenses. Marginal cost is the cost of producing one additional unit. This matrix helps managers make output decisions, especially when determining how many units to produce to maximize profit or avoid losses. These graphs bring all these concepts together. The MC curve cuts through the AVC and ATC curves at their minimum points. When marginal cost is below average cost is falling. When it's above, average cost is rising. This interaction tells us the most efficient output level. Firms should aim to operate where MC equals ATC or MC equals AVC to ensure cost efficiency. These curves also show when to stop production, like if MC exceeds the price customers are willing to pay. Now, let's distinguish between fixed cost and sunk cost. Fixed cost can be often recovered if production stops, like subleasing a building, selling unused equipment. Sunk costs, on the other hand, are unrecoverable. An ad campaign you already ran or R&D on a failed product. Those costs are gone, and here's the key. Sunk cost should never factor into future decisions. This is known as the sunk cost fallacy, and avoiding it is essential to rational business planning. In the long run, all inputs are variable, meaning firms have full flexibility to adjust their production processes. These are no fixed costs. Everything is open for adjustment. Managers can expand plant size, redesign workflows, or adopt new technology. This is where firms look for economies of scale, trying trying to produce more at a lower cost per unit. Long run cost planning focuses on efficiency optimization and strategic positioning. It helps determine whether to centralize, outsource, or automate part of businesses. Here we see the L long run average cost curve, which shows the lowest average cost at every output level when a firm can fully adjust all inputs. This curve forms an envelope that touches the minimum point of various short run average cost curves. In the beginning, you may have economies of scale, where costs drop as output grows. Eventually, you reach constant returns that to scale where cost remains stable. And beyond that, these economies of scale may set in, where average costs start to rise due to complexity or inefficiencies. Understanding this curve helps firms choose the right scale of operation. Diseconomies of scale. Let's explore diseconomies of scale, a core concept in the long run cost management. When a firm increases production, it often experiences lower average cost per unit. This happens due to several factors like labor specialization, more efficient use of equipment, or bulk purchasing of materials. For example, Amazon reduces shipping cost per package by consolidating deliveries. This cost saving effect encourages firms to scale up as long as efficiency increases. Outpace complexity, economies of scale are critical for gaining market share and improving profit margins. Real world example of scale economics. Let's Tesla gigant Tesla's gigantic factories reduces battery production cost through massive scale demonstrating. McDonald's achieved low unit cost by standardizing its operation globally and buying ingredients in bulk. But contrast with this with many government agencies, they often suffer from diseconomies due to bureaucratic complexity and inefficient processes. This example shows that scale is powerful but must be managed carefully to avoid spiral costing. Modern businesses rely heavily on data. They use historical data, production data to model cost functions more accurately by applying regression analysis. They separate fixed and variable components and predict cost behavior at a different output levels. This allows for precise budgeting, better pricing, and smarter investment decisions. For example, a manufacturing firm may use this data to simulate the cost impact of increasing production by 25%. This approach shifts decision making from intuition to evidence based forecasting. Now, let's consider firms that produce multiple products, say printers, ink cartridges. A multi product cost function captures how costs vary with output level for multiple goods. Why does it matter? Because these products often share inputs like labor or warehouse. Understanding how these shared inputs affect overall cost allows manager to plan product mixes more strategically, allocate resources effectively, and avoid mispricing. Multi-product cost analysis help answer should we produce both products together or separately. Closely related to Closely related is the concept of economies of scope. This occurs when producing two or more goods together is cheaper than producing them independently. Think of Disney. They produce movies, park attraction, merchandise, all that all of them use the same characters, brandings, and marketing teams. This shared use of inputs reduces overall cost. Economies of scope are especially useful for companies looking to diversify without increasing their cost. They enable synergy, brand expansion, and resource efficiency. Cost complementary take things a step further. It means that producing more of one good actually lowers the marginal cost of producing another. Consider Google. As more users use their search engine, it becomes cheaper to deliver targeted ads. The same infrastructure support both services. Another example is Netflix. The more content they produce, the cheaper it becomes to retain and grow subscribers. These relationships are gold for managers because they can design systems where growth in one area enhances performance in another. Let's revisit Disney as a comprehensive case. Their Frozen movie, I'm sure everyone must have heard of it. For instance, their Frozen movie wasn't just a film. It became a merchandise empire, a theme park ride, and a streaming asset. This is economies of scope in action, but it's also an example of cost complementarity. The success of the movie lowers the marketing cost for merchandise, boosts theme park attendance, and drives streaming subscriptions. By leveraging intellectual property across multiple platforms, Disney maximizes return on content creation while minimizing marginal cost. So, what we can take away from all this as managers? First, increasing output. Let's ask ourselves: are we minimizing cost while maintaining or increasing output? Second, use tools like ISOCANs and ISOCOST to evaluate input choices. Third, analyze whether producing multiple products together lowers total cost. Finally, use data driven to model cost accurately and make evidence based decisions. Strategic cost management isn't just about saving money, it's about enabling growth, pricing competitively, and sustaining long term profitability. Let's wrap up today. Today, we explored the production functions, short, short run and long run cost structures, cost minimization strategies, and the role of scale and scope in shaping a firm's cost efficiency. We looked at how real world companies from Tesla to Disney apply these principles to drive successes. These concepts are not just theoretical, they are practical tools for managers like you and me. Thank you. And finally, thank you so much for your time and attention. I would be happy to answer any questions or hear your thoughts on applying these insights in your own industry. Thank you.